We do a lot of binary encoding in Go. What is binary coding? If you're not sure why, it's well, I would say it's interpreting sequences of bytes in standardized ways. Other people would have different definitions, but essentially you're turning your structs and information into binary. In terms of why we do it, we want to work with data sets that are larger than RAM, and we want to reduce the garbage collection pause as well. So one of the nice things about memory mapping is that it's not a garbage collected region, so you can have huge data sets without incurring the penalty of garbage collection. So our goals are a bit different to some, but speed is really important. The space is really important. And we also want access to partial records, which is something that only a few of the different encoding formats support. In terms of considerations, we have a lot of read and writes, more reads than writes, but a lot of read and writes. Our data format doesn't change too much. And like I said before, we actually want access to the data in partial formats. So sub items of each record without actually having to decode the entire records. In terms of what you can do with binary encoding, these are the things that aren't so important to us, and they might be for other people. So bear that in mind in the way that we're doing this talk. So there's a few different options that you can do for binary encoding. There's some built-ins that you can use. There's a whole bunch of packages that work on reflection and field tags. Then there's more advanced ones that use compilation of custom schemas, and then you can choose to do your own encoding format. So we're going to run through each of those. In terms of why we do it, this is just one sample and simplified use case that we do, but we do search and matching, so things like similarity search, and we may want to calculate the similarity of one document against millions of others or hundreds of thousands of others. And so for us, a search query can be a document. It doesn't necessarily comprise one or two terms. It might comprise thousands. And when we're doing reads, we're actually looking at the union of all of those. And so the actual amount of reads that you have to do is really high if you want to keep that in real time and not start caching things. And typically, because you have really large vectors as input queries like documents, you can't actually cache a lot of stuff anyway because they're all different. So this is just an example that we're going to run through in terms of us as a input query with 1,000 terms, some meta parameters, and we want to actually get a response time from that on a single node against 500,000 documents in 100 milliseconds. So that's just one of our internal goals. In terms of what we need to do, it's about 1.75 million reads. There's a few different sizes, but for simplification, you can think about the sort of read speed that you need, and we're getting down in around the 100 nanosecond region per record, that's on my laptop too, but that's starting to get pretty small. We have different options to make that more palatable by using more CPUs and reading concurrently, or we can also try to read less, which we do anyway. And the other thing is to speed up the decoding. So that's what we focus on as the first thing. In terms of how that affects us, it might be a bit small, but it's just showing that if you spend a lot of time decoding and reading your records, it costs you a lot when you start to read millions of records. And so for us, a write might update hundreds of records, and that can be relatively fast, even if your encoding is quite slow. But if you need to read millions of records, then suddenly it gets quite difficult to do things efficiently. And if your decoding is slow, then that becomes a big issue. So in terms of options, there's built-in binary encoding in Go. So if you haven't seen it, the package is actually there ready to use. And the code that's shown there is really all you need to do. Your struct is actually your struct or whatever you want to encode. things to note about that is that it only supports fixed size fields, so you can't put things like strings in there, and you lose a whole heap of the other benefits that you get with some of the other encoding messages. And it also uses reflection, so it's not that fast. GOB is something that's unique to Go. It's really interesting for certain things, but not really applicable to what we want to do. It's self-describing and really good with streams, but that's not really what we're dealing with. So there is some overhead, but in terms of getting it up and running, again, the code's pretty simple to get that up and running. In terms of external packages, if you start to have a look around, there's heaps. There's 15 that I could find pretty easily, but there's probably a whole heap more. And from what I can see, and other people might correct me, but they all tend to work in three different ways. The first one is you add field tags to your structs. So for those new to Go, that means you're adding a little bit of identification information to each field in your struct. And essentially that gives instructions on how to encode things to the encoder. So those have the least changes to your code, but on the flip side, they're not that fast either. So the second option is to actually compile encoding code from your code. So that essentially looks at your data structure and creates code that does the encoding for you. So that's actually quite a bit faster, and you can use your structs as your data format and compile the code that you need to do your encoding. The third one is actually to start with custom schemas, and that you're writing schemas in different formats that don't fit inside your Go code, and then you're compiling them to produce Go code. They're the fastest of all three, but the thing that you lose is you kind of lose the Go-ness of everything, because you have to start looking at your data as bytes and methods on bytes. So you don't actually get to do all the nice things that you can do with your structs in Go. Is it worth the effort? For us, absolutely. But these are some benchmarks that were done by Alec Thomas, and he's got a benchmarking suite in GitHub, which gets updated as new encoding formats come out, which is interesting. But the thing to note is that it's for this struct that you see in the top here. And so it's a pretty simple struct. It doesn't have nesting. And so for a lot of the serialization, you find that when you start to nest different structs and vectors inside, that you start to get funny things, and they don't act as you would expect them to. But they're a good set of benchmarks to give you a basic idea of how long things take. This page is the first set, and then there's more on the second page. Keeping on here, the two to look out for are Flatbuffers, which has the fastest decoding, and protobufs, which is, there's two different versions of two different packages of protobufs, Go protobuf and Go protobuf. So if you're wondering, it's not a spelling mistake. Go is faster and has a few more options. I don't know if it was intended to be written that way, but probably. And so they're probably the two that we see as the two fastest in these benchmarks, which is a good place to start. So looking, compiled, definitely faster. Go protobuf is really good. I'd really recommend it for different things. Flatbuffers is really fast to decode, and you also get zero copy access to your structs, so zero copy access to your data, which means there's no intermediate allocation to access your data, which is really useful if you want to be fast and you don't want to create garbage. So Flatbuffers, obviously pretty good. And the other thing that I'd note there is that Cap-n-proto is not in that list, but Cap-n-proto is pretty good. So we're going to focus on that as well because we've tested it. So the two that we really focus on that we think are the fastest outside of Go protobuf, and that's specifically because we can't do the in-access reads in Go protobuf. You need to actually do a decode to start accessing your data. which is a bit of a killer for us. So the two that we're focusing on are above. The Cap-n-proto. Does anyone use Cap-n-proto? 1, 2, 3. Okay, 3 people, so not many. It's kind of a weird name. There's some funny discussions on it because a lot of people actually thought it was a joke. If you see their homepage, it talks about serialization, like breakfast cereal and other things. So you'd look at it and not really take it that seriously. But the guy who was behind it was actually primary in protobuf 2. And one of the nice things about it is that it has RPC built in. So for sending information over the wire, and some of the advantages are that it knows how to compress information to make it efficient for sending over the wire, but also has a bunch of other security options and things like that. So this is his assessment. So Cap-n-proto does pretty well, obviously. But also you see that protobufs are pretty good as well. SBE is not available in Go at this stage, and Flatbuffers obviously is, but is relatively new. In terms of what it looks like for Cap-n-proto, you have to write a schema like the one you see there, and then you compile the schema. So you run a compiler and it produces code like you see below. And so that gives you access to your data. You can, but instead of having your struct, you end up with the Cap-n struct and all the methods on it. So when it comes to doing your code, you have the choice that you can either convert all the information back to your structs but waste the time, or you can use the methods to interact with the information directly, which is much faster from a read perspective. And then there's another package associated. It's a Go package for Cap-n-proto, which is called bambam. And bambam essentially creates your Cap-n-proto schema for you. So you just point it at your Go files and it will come and create your schema, and it'll add the field IDs to your structs. And then you run Cap-n-proto to compile a schema. So it's a 2-step process, but you effectively means that you don't have to do much and your code is transformed into all the code that you need. And the field tags on here, the numbering also means that you get backwards compatibility. So if you come and add a new field later on, that doesn't break things, which is pretty important for most. Yeah. Yeah. So you'd add the field in with a different ID, or if you add a new field, it wouldn't have an ID. So when you run it, it realizes that field doesn't have an ID yet. It knows what the counter is, so it adds one. Yeah. So if you want to wipe it and start again, you delete all the field tags and start from scratch. So for us, in terms of benchmarks, the term struct is got quite a bit of nesting in it. The rev struct doesn't. But my notes on this is a full encode and decode. So this is not accessing the data directly, which is not the smartest way to use Cap-n-proto. But the one thing I'd say is that if you're using bambam and Cap-n-proto, you end up with boilerplate on boilerplate, and you start to try and look through to understand what's going on, and it gets quite annoying. So you have the choice to give up your structs altogether, which is what I mentioned before, and in that case, you never convert back to your particular structs and data format. Your data is stored in binary with methods on binary, and that's how you do everything. In terms of zero copy, so that's comparing at the top the two methods. The encoding step's the same, but the decoding step obviously much faster, more than 20 times faster. But like I say, you don't get your struct back, so it's more difficult to have methods and things. You can do it, but you need to think about design a lot more, and it's a bit more complicated. And then the other thing I'd note is that the Go version does allocate. So I don't think that the Go version is efficient as some of the other languages yet, so it'll probably improve. So in terms of Flatbuffers, which is the other one we're looking at, that's created at Google for high performance applications, it has the access to raw data without unpacking, which is something that we really wanted. You get a reduced schema set. So instead of sticking with the types that you're familiar with, you have to think in terms of the ones that they provide. And then the other thing is that it doesn't do everything for you. You still need to do quite a bit of code yourself, which is different to Cap-n-proto, which does most of the code for you. So this is an example of a schema, which is equivalent, same, custom schema sort of style as you use for Cap-n-proto, but the namespace ends up being a Go package. So if you have multiple objects, you end up with a package with all different files, and each of your different objects ends up with its own file. So in terms of what they look like this. So you end up with this table. Flatbuffers table is your struct and all the methods on it. So you compile that and you end up with Go code. So that was the Go code that I was just showing you, is compiled from the schema. But the thing that I would note is that it doesn't do everything for you. So if I was to look at, so for our normal term struct, which looks like this, it's got these three components in it. This is what it takes to do it in Flatbuffers. That's all one function, which is pretty annoying. Doesn't work. And in fact, there's things with this that aren't working now that I'm waiting to get responses on. And part of that's because there's not examples for nesting vectors and things. So there's a few strange behaviors, but it doesn't create all the code for you. But the other thing to notice here is that Flatbuffers works from a leaf perspective up. And so you don't create your parent object and then create all its children and their children. You have to go to the very end and create them first, and then create the parent with the children and then the parent. And it's just a little bit backwards in thought. It takes a little bit of getting used to, because it's just different to how you do things. But the amount of code that you need to do a nested vector version starts to get quite high, because things like strings are actually a vector in themselves. You can't, if you have a string in another vector, you have to create the string before you put it in the vector. So it's just, it's quite complicated. No, it's all right. It's not. I think if your structs are very regular and you don't do a lot of nesting, then it's pretty cool. As soon as you start to nest things and you have strings and variable, it starts to get complicated pretty quickly, but in both ways. Yeah. But in terms of how it performs versus Cap-n-proto, easily faster for full encode decode. In terms of the downsides, I've discussed them a little bit, but the leaf node up is just a little bit backwards. It takes time to get used to. I think the API is going to change. People, in terms of Go, it's relatively new. People are still debating a few things, and there's not a lot of examples out there for the nested stuff. So it's a little bit difficult, but you get the speed. So if you want speed, then it's worthwhile. So in terms of those, we look at how fast they were and then start doing benchmarks to see if we could actually do some of our own encoding. And mainly that's because we have different demands. We're not used in the same ways. We don't need all the features that they have. So we think that we can make things faster if we do it ourselves. So our key goals with that are to allow for future changes, but not at a message level so much. So more of a global style. And we definitely want zero copy access, and we prefer to be able to encode and decode maps, which is not supported by Cap-n-proto or Flatbuffers at this point. And in actual fact, it's pretty slow to encode and decode maps anyway. So I'd advise people, if you can avoid it, don't bother. But we had some legacy stuff that we needed to use it for. So what we did is a little bit similar to Flatbuffers in terms of, when I saw Flatbuffers and I actually had a look at some of the Go code, I was thinking, yeah, that's pretty similar to what the way that we do things. But essentially, you think of everything as a byte, and you have methods to read and write to that byte. So this is just an example with uint16 on how to write it and how to read it. But the nice thing is you read it in place, so there's no copying involved to access that. On top of that, we add some other additional methods. So this was just an example, which is a little bit overkill, but it's just showing that you can encode a map string with different key sizes. All of these things use a similar approach in that the elements that are variable size, they create tables at the start that show how long each element is, which gives instructions on how to unpack it. And so we do a similar thing. If you have a map, you basically write the lengths and the offsets of each of the things up front, which enables you to decode them all in sequence. So one of the interesting things for us, instead of packing some of the table information inside the message, each different object that we have becomes a package in itself, and we define essentially offsets for all the fixed information, and then we have our own methods to compile the non-fixed information after that. So it means you don't need to put a lot of decoding instructions in the actual binary encoding itself. And it also means that when you're accessing any of the fixed size stuff, you can read it directly without actually having to skip on to any offsets or look up where it is or how long it is and things like that. So it looks a little bit like this. We include a version. Our benchmarks show that the switch is pretty negligible, so we went with this option. Essentially, it means that in a package for a given object, we can change the data structure and we can encode and decode different versions and convert them to and from each other really, really easily. The other thing to note here is that we basically go and check the size of all of the different elements that are variable in size up front quickly, and then we use that to work out exactly how much size to allocate. So we do that one large allocation that's going to be exactly the size that we need, and then we write all the data to it. So it's quite efficient. We could have done this method a little bit differently, but I'll explain that in a sec. Essentially, we've separated the storage, which is the memory mapping component, and the encoding, decoding. So our storage package is just, it only cares about binary. It doesn't care about what you're uploading or getting. So you can throw any object that satisfies the encoder interface, and the storage will know how to decode it and encode it, just put it in, get it out. We didn't, one of the things you might notice is that if you put the byte inside the encoding as a function variable, then you could write without actually creating any data at all. But the reason that we don't do that is because our storage, we can't guarantee in our storage that we will have a sequence of bytes long enough to actually write the object. So instead, we create it to a byte slice, and then we upload it in and copy it. So the good thing is that all the encoding happens in line. So there's a few comments out there that one of the disadvantages with Flatbuffers is because you have so many different function calls and methods in a row that don't get inlined well, the encoding time really, really suffers. And so one of the nice things for us is that we can put all of that in one function so you don't have that overhead. Things like the table pointers that can be part of the actual object itself, we don't put them in the object, we declare them at a package level. So essentially the package knows how to understand a lot of the data without needing to put that information in the data itself. So that saves us quite a bit of space on each record. And of course we can support more types and also convert between the different versions that we have. Downside, making changes is a little bit more complicated. One of the nice things of the other packages is that they do track the fields for you. So if you add a new field, it goes at the end. It doesn't mess up with the existing data, which is nice. But for us, we really don't change data much. And if we do, we just write a converter and we'll stream one file into another and quickly convert it to the new format. So for us, on balance, that's a better way to do things. We don't handle streams, which is another thing that Cap-n-proto in particular is really good with. And the other packages also come with a lot of other options that we don't support but don't necessarily need. In terms of benchmarks, we get quite a bit faster than Flatbuffers, 6 times faster encoding, which is not surprising, but also faster decoding, which is good. And in terms of packing size, there's a question mark on Flatbuffers because at the time when I did this, I couldn't actually get the full nested encoding working. So I don't even know what it is yet, but I'll have it soon. I'll update it when I put the talk up. But in terms of size, by doing your own packing and omitting some of the table information, you can get much smaller sizes in terms of the encoded data. In terms of the example that we started with at the start of the talk, the 1.75 million reads that we wanted to do, there's a few different objects that we need to read. So they're the 3 different rows here. And effectively for the rev, we're getting down to around 20 nanoseconds per read and 0 allocations per read as well, which is another one of the important things. So because we have access direct in, we don't need to do any allocation. So if we want to read 1 million rev records, we allocate the 1 rev record and then we continually just push more data into it. And so we don't need to do any allocations to do a lot of reads, which is good. And so in terms of where we got to, on a single CPU, we can get those 1.75 million reads in around 135 milliseconds. So it's down around the 80 nanoseconds average, which we couldn't get with any of the packages that we tried. So I guess in summary, I think Cap-n-proto is good for streams and zero copy as well. Flatbuffers is also good for zero copy. I think Flatbuffers will probably end up being faster, but some of that may be due to the different way that the Go versions of these are written. Either of them may not necessarily be as efficient as they can be. In general, if you want to get fast, you pay for it with complexity. So if you don't need the speed, don't bother, because it just makes all your code a little bit more of a mess. You have to think through things a lot more. And the other thing that was surprising for us, if we look in terms of the code that we needed to write our own encoder, it probably ended up less than some of the code that we would need for some of the packages that we needed to use. So it's a consideration if you want to write your own. That's it.